along with the axiom of infinity, it provides a good segue for us to make a quick digression into some metaphysical and epistemological questions, because
Okay.
the axiom of the empty set quite literally asserts the existence of a set that has no members, and the axiom of infinity quite literally asserts that there is an infinite set. And
Mhm.
I'm guessing that you would describe yourself as a mathematical Platonist, and that you believe that
Yeah.
there exist, in some sense, these mathematical objects. And I'm just curious
Yes.
how you would explain what you take to be your justification for believing that there are these sets, which are clearly so important if they're to form our foundation of mathematics, when you also presumably cannot see them, touch them, hear
Right.
them, this sort of thing.
Right. Yes. Okay. Yeah. Yeah. Sets and in general, all mathematical objects are, of course, abstract objects. They don't exist physically. Um, However, they do exist as abstract objects, and the way I see the universe of all sets as existing is not different, not very different from the way we see the counting numbers existing. I mean, the let's start with this. So let's start with the counting numbers: 0, 1, 2, 3, 4, and so on. Okay, those are those. I don't think anyone would deny that numbers, natural counting numbers, or at least up to the numbers that people have ever counted to, right, which are only finitely many, that those numbers exist in some way, right? It's not something. It's not something invented. It's something that is part of the world. I mean, um, on this table in front of me there are 5 books, right? Not 4, not 3. Being 5 is something that I'm not making up. It's some property of those objects on this table, right? There are 5, not 6, not 7, and so on. So the counting numbers do have a reality, do have an existence that I think most people would agree on that. But now, when one looks at the natural numbers and starts studying them, one realizes that, of course, that there is no last natural number. They go on and on forever. So this is an infinite set. Well, I mean, some people wouldn't call this a set, or just a potential set, right? I think we should not go into the long debate between potential and actual infinity. But okay, but anyway, so there are infinitely many natural numbers, and those natural numbers have very specific properties that we can study. Those are what we call arithmetical properties. We have basic operations on them. We have the sum, the product, and so on. They are ordered in a certain way. Okay, so this is a mathematical structure that is very well understood, and you don't have to be an expert mathematician to understand the basic properties of it. Now, with set theory, things become a bit more complicated, but they are not essentially different. I mean, in set theory, we have this very basic notion of set, and I would say you cannot think of a more basic notion than the notion of set. If you try to explain what a set is, it's impossible. You have to, you go in circles. Even Cantor, when he first tried to define what a set is, he says that the set is a collection. Well, then what is a collection? I mean, there's no way. I mean, I've never seen any definition of set that doesn't somehow include itself, right? That is not circular. So the notion of set is so basic, is so simple that I cannot think of a simpler notion than that. So, but if you start with this basic notion of set, and then you look at these basic operations with sets, of taking subsets, of taking unions, of taking pairs, and so on, then what you come up eventually is with this view of sets that form the von Neumann universe. And this and the way it's defined or constructed, as I explained before, that you start with the empty set and keep taking the power set at each step. When you reach a limit, you take the union, and so on. So this is a very well defined, very well described mathematical structure that you want to study, that you want to see what properties it has, how far does it go, how big is it, how complex is it, and so on. And then you have these theories, Zermelo-Fraenkel, that describes this structure to a certain extent. And that's what set theories do. They use this theory to study the properties of this universe, set theoretic universe. And we know that this theory is insufficient, that there are many questions, some very simple questions that this theory does not answer. And so this prompts the introduction of new axioms for this, and so on and so forth. So this has, to me, and I would say to most people who work on this structure, this mathematical structure, does have a reality. It's not something that is arbitrary or invented. No, it has a reality in the same sense that the natural numbers have a reality. And in the sense that, so it's part of the universe out there. So I don't see much difference between the natural numbers and the set theoretic universe, essentially.
Mm-hmm. What you've said reminds me a great deal of something Joel David Hampkins said, I think both of the times he's been on the podcast, in that he finds the existence of the empty set to be much more obvious than, or much more clear than the existence of, like, the cup he was holding at the time.
Right.
And what it sounds like to me is that you're saying you have far more ready and available insight and access to the properties of sets and the universe of sets
Right.
than you do to, like, the existence of this phone. Like, the physics of this is very, very mysterious. You're not certain of any
And
properties of it, really.
right.
Quantum mechanics. Yeah.
Mm-hmm. Yeah, I mean, physical
So,
objects are extremely much more complicated and much less understood. So, and in this sense, they are a lot more mysterious than the mathematical objects we deal with, which are perfectly defined and determined, and they are there, and they don't change. We can study them in a very precise manner. We can prove theorems about them. So our knowledge of those objects is far better, a lot better than the knowledge we have of physical objects. And in this sense, and I agree with Joel, in this sense, their existence is more obvious than the existence of physical objects. So it's more clear that they are something, that there is something there with very definite properties that we can understand perfectly well. Whereas for physical objects, who knows?
mm-hmm. And something else that I think Joel and others have said, and maybe you've alluded to as well, is that there's a certain richness and utility to the set theoretic framework, though imperfect, that ZFC comprises,
Mm-hmm.
that makes you believe in it. The fruitfulness of it. It couldn't have been this fruitful, couldn't be the foundation for all of mathematics if there weren't some deep truth to it, if it did not exist
Right.
in an
Right.
abstract way.
Yeah. Yeah.
Okay,
That's
so that's also, you'd say that's also accurate.
right. Right. I agree with you. Yeah. Yeah. Yeah, I would say this. Yes. It gives
Okay,
additional,
great.
the fact that it's not fruitful, it gives additional support to to not only to it being true, but also to being the right theory of sets. Yes.
Hmm. Okay, then the last thing I'd like to get back to while we're on this little digression about maybe metaphysics and epistemology is why you mentioned earlier that you think of set theory as the general theory of truth.
Hmm. Yeah. Well, I mean, um, it's this has been said before, and not maybe not for set theory, but certainly for mathematics. I mean, um, uh, I was in a talk not so long ago by Martin Brightson, a very famous British mathematician, and he defined mathematics as a vast exploration of truth, and I entirely agree with that. And set theory, insofar it's the foundation of mathematics, so it gives you the it's the foundation, it's the basis of mathematics, and therefore, if you view mathematics as an exploration of truth, then set theory is the foundation for that. So the it's I think that set theory is I would say I'm a logicist to a certain extent, probably to a full extent. I believe set theory is part of logic, and it's part of the and logic seen as the uh, part of as the theory of investigating truth, and how truth, what is true, and how truth is preserved through reasoning and so on. So set theory is also part of that, and so I'm interested. In contrast with Joel, for example, I think, and let me be a bit polemic here. Um, um, I I think that the goal of set theory is to study the set theoretic universe, which I think it has a precise. It's a very well determined abstract entity, or mathematical entity, and our goal is to study this universe, in this universe is where all happens. All mathematical happens there, right? Now, Joel has a more playful approach to set theory, what I would call a playful approach, because he likes to investigate all sorts of different models of different theories of sets and so on, and he he plays with them, and he proves great theorems about them. I mean, he has a fantastic work in set theory, as we all know. But his view of sets is very different from mine, because I see all he does as happening inside this uh, inside V, the true universe of sets, where everything happens, right? So, if you want, when I say that set theory is the theory of truth, is because if you make any statement in mathematics, not only in set theory but in mathematics, and you want to know if it's true or not, well, how do you know? Well, uh, you have to prove it. And what does it mean to prove it? It means you prove it from some axioms using logic. And how do you know those axioms are true? Well, ultimately, the test for what tells you, the theory that tells you what exists and what is true, is set theory. That's the bottom of it, right? I mean, you what if you do whatever If you work in any area of mathematics, you work with topological spaces or algebraic structures. How do you know those exist? Well, you go to set theory. In set theory, you can build or you can show that those structures, or at least something isomorphic to them, does exist. You prove it. You prove that those objects exist. And then just by using the axioms of set theory, you can prove theorems about them. Yes. And that's how mathematics works. And this is how mathematical truth is warranted. You can only say that something is true in mathematics if this can be done, at least in principle. I mean, usually it's not done. Usually mathematics work in their own fields, using their own local axioms or ideas and so on. But this grounding is can be done in principle. So if someone has doubts about the truth of some mathematical statement, well, you have to analyze the proofs, see what objects are required to exist for this to work, see if all the reasoning is correct, and ultimately you can, if one has enough patience or enough will to do that, one could in principle formalize all this into the language of set theory and then check in set theory that this is indeed true. So ultimately, mathematical truth is based on set theoretic truth. And this is why I'm saying that set theory is ultimately the theory of truth.